Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our today's webinar, Retaining Wall Failures. My name is Megan Purdy and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures and to elders past and present. Before we get started, I would like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Brickworks. Brickworks is recognised globally as a leading manufacturer of quality building products, including bricks, blocks, retaining walls, pavers, natural stone, wall cladding, facade systems, roofing, and so much more. Their brands continue to build their reputation for delivering quality and lead the industry through style and product innovation, creating impressive materials designed for inspiring built environments. We thank Brickworks for their continuous support. Now today we will hear from our two speakers followed by our live audience Q&A. So I encourage you all to please send your questions through to our speakers via the chat box. I'd now like to welcome our first speaker, Andrew Middleton. Andrew is a senior principal engineer with 40 years of experience in Southeast Queensland. His career spans major infrastructure projects such as the Gateway and Logan motorways, the Port of Brisbane and the Southeast Busway, along with significant land development and building works including early Springfield developments and the Gabba upgrades. He brings both deep practical insight into ground risks and solutions, particularly on challenging sites. Please join me in welcoming Andrew Middleton.
Well, thank you for that introduction and welcome, and thank you for attending this talk. Obviously, it's quite a popular topic. So my name's Andrew Middleton, as you can see there. I just wanted to start by adding to the acknowledgement of country and my own acknowledgement of the traditional custodians. I always like to say, you can see in this image a gawky, geeky 14-year-old with some 4 generations of links to some land and some country out in our west, and I think that's important that we all acknowledge our, and especially us geotechnical people, as you know, we're in the soil. I just want to also acknowledge some previous work that's been done and presentations done on this. There's a great presentation that Chris Haverford particularly did some years ago, and you'll see that there. And some good, really, it's a great paper by Mike Davey, who's only just recently retired. Some excellent resources there that you can refer to. Failure. Obviously, we're here to talk about failure, but I really just want to define that failures, as you can see, it's about growth. It's about mindset. There's no judgment implied or in this talk today. We're here to talk about how we can take away lessons and as a profession together get better at what we do. So it's success and progress, and here we are. It's good to have you along for this as well. So this is a few lessons that I've come across in the last few years looking at helping people where there's been problems with some walls. So it can happen, and I've always been told and learned from my mentors and acknowledge them that it can happen to anybody. So the context that I'm going to be talking about, the other speaker will talk about deep walls in cuts. I'm going to speak about deep fill walls. So that's a particular area where we're noticing lots of concern and lots of issues. So the context, obviously, why we're probably seeing a lot more of these walls in land development, and that's where we particularly see a lot of work happening and a lot of concern. I would say the transport industry is well ahead of everybody in terms of the standards they adopt, and they rarely have problems. So the context is obviously land is valuable right now. Every square metre matters. Topography is a factor. Less big walls probably in some other capital cities compared to Brisbane, particularly. I'm coming from Sunshine Coast up here. Topography largely is even residential land, it's what we want. We don't want big walls next to houses, so we put big walls on the perimeter of housing developments or land developments, so that we can keep land, the steps between blocks at a reasonably small height. So the other context of, certainly from where I operate, a lot of poor quality soils. There's not a lot of good land and there's not a lot of good soils, unless you're brownfield, but certainly greenfield, obviously there's less choice. So, the other thing, obviously, it rains a fair bit. We're subtropical in Queensland, but if you look at the rainfall intensities and the charts, I think it's easy when you look at, say, the annual rainfalls there, it's quite easy to become complacent and probably somewhat comfortable with what you feel is a reasonable amount of rainfall. But many Queenslanders will certainly remember 2011 and being quite a major. Some will remember 1974. You can see the spikes on the curve, but 2022 doesn't ring a lot of alarm bells. But in fact, you can see that a very severe spike there, and we received a metre of rain in just 5 days. So, continuing to appreciate what it is we've got to allow for and design for is I would say, don't get too comfortable. Always remember nature. Nature's variable, and you just need to keep in mind those are the kind of things we need to be looking forward to. And design is about the future. They haven't built it yet, so we're going to look a long way in the future. So I think it's just good to stay objective about this, and this is the kind of thing. Data is what keeps you objective. So infill, typically you're building to your boundary, of course, and we will find that therefore that the land that the toe of the wall will sit next to is your neighbour, is not yours. So walls in cut, the toe of the wall sits towards well, in both cases it's in your land, but in the case of cut, the land below the wall is yours. In the case of fill, it's not yours. This changes some things that you can practically manage, or your client or your owners can manage in the future. So the types of walls that typically we'll see used is obviously you can cantilever, sleeper, or post and panel. Obviously, panels are becoming more popular than sleepers. More traditional, I suppose, cantilever, concrete footing with blockwork or din sill systems. Your mass gravity walls, obviously you can see a selection of those along there, coming either what I call natural facing, cut sandstone, or in the case of Brisbane, granite. There is a significant granite supply available. Then you get your engineered walls with the big, large block format facing blocks. There's a number of products out there in the market, and then you get your mechanically stabilised earth, MSEs, the GeoGrid products, which go in combination with some or even potentially all of these, apart from sleepers. So those are the kind of walls where there's a lot going on, and we're noticing a bit of a pattern of some issues to do with this. So I'm just going to, of course, if you want wisdom, you just go to AI, of course. So here's what AI, which is a summary of what the internet says. So poor drainage, obviously I won't read them out, but just to say water is, at least half of those are related to water, whether it's surface water or groundwater. Obviously, there's then design, overloading, whether or not that was intended or missed in design, and obviously materials. Typically, though, water is by far and above the major. You can see a couple of little failures there. You can see the gentleman there. That's actually not from Australia, and that gentleman is a politician, and you can see he's educating all of us about there's been a big wall failure. So slow news day, perhaps, I don't know. So anyway, it will make the news, and we don't want that to happen. Okay, wall design, AS4678 has a great summary. So wall design, there's eight different modes you need to consider. 5 in terms of the ultimate limit state or failure modes, I'd call them, and another 3 in terms of serviceability. You can see those there. Wall design, I don't know too many other aspects of engineering that have so many aspects you need to consider in wall. Wall design is not simple, it's not easy, and it includes an interaction between both structural elements and soil. So it is quite a significant bit of engineering work, and as you get big walls, you get very, very big loads. So I think these are amongst some of the most the significant engineering structures that get built. So again, just a basic earth pressure theory, passive on the leading side of, say, a cantilever wall there, active earth pressure on the back, provided the wall can move. The wall's restrained from moving, you would use at-rest pressures which are higher. Obviously, there's an increase due to surcharging and whether or not there's water. In a high level, typically they're mass gravity type walls, you've got sliding. Nothing new there, just giving that summary, just to have a look at what we've got. So one of the things about FARs is we often get to do testing, and my guess is 10 times the testing you would do for the original investigation and design. So again, as I say, we have to be careful about judging others in retrospect, because with the benefit of both hindsight and lots of testing, it's easy to do that. So this particular project was quite useful in that we were able to obtain quite a number of triaxial strengths tests. What was good about that was it indicated that the design parameters fell within the range of average fill for the material. It was well compacted. You can see the grading particle size distributed, well graded sandy clay material. So that was good. That took that variability out of the potential what was going on. I'll just note this is an issue certainly for Queensland tertiary soils in Brisbane, or tertiary rocks, very poorly consolidated, fissuring and micro fissuring type blocky structure means you get very low cohesion. Just have to be aware of that. Obviously, if soils get wet. The other thing that we're able to usefully learn from this project is there's a correlation from Sorensen and others on friction angle with plasticity index. What we've found is that for us, at least in our Brisbane soil, slightly overestimates 5. But again, it does show that there's a reasonable field correlation there. Not a bad way if you've got data to start to make some reasonable estimates. So obviously, the table from AS 4678 is always a good guide. Wouldn't go far from that at all. So that's good. One of the factors we do find, obviously because of the high rainfall we've been finding in walls, is, and this is some of the work, Mike Davies' paper shows this chart here. You can see showing we have high soil suctions in the upper part of embankments or clay embankments. And then as you get deeper, you tend to get down towards water table, and you then find that you go into, instead of soil suction, you go into positive pressure. Of course, the benefit of high soil suction is it gives you high apparent cohesion. A lot of embankments and a lot of cut slopes stand up in the short term because of these suction pressures. But of course, as water becomes available potentially to that suction, the suction will draw in water, suction will dissipate, and there'll be a loss of that apparent strength, apparent cohesion with that, and you need to account for that. What we're finding interesting is, for example, where there's a grassed area, you can see down to there about 2.5 to 3 metres, you can see effect of the moisture profile where it's in the grassed area versus less effect when it's in the concrete. And that's actually not that's not a surprise. I think that should be assumed. But of course, what parameters you should assume should reflect that. What was interesting is that kind of shows the same pattern that was published for that London clay, where we've got the reducing strengths at the top, low, and going with depth. However, I will add a caution. In the bottom right was a deep fill site, and you can see deep wetting has extended down to nearly 8 metres, 7 metres of fill. That is a result of fill that's generally placed dry of optimum. So typically we specify a compaction range, a compaction density or dry density ratio of 98% with plus or minus 2% moisture range. The reality for compaction is that it's easier, you to compact drier soils with less moisture because you've got more air voids to work with. So it's going to happen. If you specify that range, you're going to find contractors will tend to push towards the dry side because it's easier to compact it. But the problem there is you get quite significant air voids ratios, and with high air voids comes higher permeability, and that allows for more wetting effects. Sodic soils are an issue so these are soils with high sodium ion contents due to natural deposition. Bit of an issue, certainly in south and southwest of the city and even north of Brisbane, and particularly as further west. Those obviously have the capacity for fines migration to lead to very rapid, deep wetting profiles. Some of these events are occurring in one storm where we're getting deep wetting because of uncontrolled surface water flows. Obviously, I've mentioned obviously things like rainfall intensity before. Differential settlement and its effect on stormwater systems and their ability to introduce, because of differential settlements, to introduce large amount of water undetected. Typically, it's not obvious until it's really way too late. Nobody's checking the integrity of stormwater. As long as the water disappears, it's good. It's good. Fire mains are a major contributor to problems in clay fields. Again, differential movement as earth pressures take up potentially leads to that. There are circumstances where there's been unmonitored water use in the fire mains and significant volumes discharged from those over a period of many weeks. And of course, it only became evident when the wall had a problem that something was going on. As I've said, with increasing moisture, you get loss of suction, your earth pressures go up. And again, you need to either reasonably allow for that or try and ensure that there are measures in place that doesn't affect it. And I've mentioned the clay fields, sodic soils. So, wall movements, we've got some really good data from a particular project where a 4 metre high wall moved. You can see the effect of the movement there. Joints opened, the concrete moved away from the asphalt in the driveway. What's interesting is different parts of the wall move differently. So one end of the wall, which is the lower changes, it was quite stiff and there was very little movement. As you go further along the wall, it increased to about 0.5% of wall height. What was also really useful is they monitored, they took readings as a very diligent client wanting to not ensure that they didn't affect their neighbour. We found that it was about 100 days for those movements to fully develop. So that's the dissipation of the soil suctions. And in terms of earth pressure theory, that's the development up towards the closer from at-rest pressures up to closer to the active pressure. And that's the wall taking up and the soil relaxing and the wall taking up movements. So this has been a really useful one to show us that, look, walls shouldn't move more than 0.5% because of safety factors, but they can move up to 1%, and that's a real number, and it will happen. So occasionally, sometimes because of suctions, if they're maintained, you won't see very much movement. You get comfortable with that, but you need to be aware that they do happen. It's a real thing, so if we put it that way. And of course, with movement, you get obviously stormwater pipes are prone to movement, fire mains, so we're going all over that. Stormwater pipes are obviously bedded with bedding gravel and they're large diameter, so they are great big subsoil drains. So we strongly recommend using a ag drain in the bedding gravel that discharges into the access pits at the end to the shafts. Blinding of that layer, I think I would probably, if it was a high risk situation with the potential to affect a wall, I would recommend blinding as well, just to help do everything you can to mitigate the risk of movement causing opening up of joints. So remember, vertical settlement will happen anyway. That's just normal. Well compacted clay fills settle upwards of 0.5% of their thickness, potentially up towards 1% of their thickness anyway. If the shaft's bedded down at a different level to the pipe, you're going to have differential movement. So the other thing I think is the potential to use smart technology to monitor water use and have some sort of alert system. I mean, maintenance people aren't aware of necessarily why this would matter, but having alert systems that indicate, say, a fire system is using an unusual, or an irrigation system is using an unusual amount of water, and that going to people who know what it means, and investigating those issues quickly and promptly and dealing with them. I think the other aspect, of course, is ensuring when there is movement at the surface, those joints which might be in pavements or opening up of joints in concrete, that those are promptly dealt with. So it's a bit, it's quite popular here for the rock walls. Gentleman on the bottom left there, you can see, is pointing out a very poorly built wall. That's an American, US image, by the way, so nobody here. It's quite popular to adopt this system where there's a facing rock, which could be cut sandstone or boulders laid in a compacted and neat way, but then to substitute a backing rock behind that. The idea being the backing rock provides a lower pressure than the soil, and it helps resist sliding. It provides mass for overturning stability. What it does do that we've found is it introduces another failure mechanism, and that's the one that I've demonstrated down below. For example, it really means that it's an internal failure mechanism that's not really, it's not the same as the one that's shown as the classic sort of sliding, and it shows the very high degree of sensitivity of the facing rock construction. It becomes really critical once you get up above, for the size of blocks, sandstone blocks or boulders that you can practically manage with most machines, and given the constraints of construction site accesses and trucks movements, once you get over about 4 to 5, maybe 6 metres, we find that the statics really starts to struggle, and you've got to do other measures, or you've got to really carefully engineer and think through how is this actually going to work. Boulder walls built well are great to look at. I mean, they're the stonemasons of this century. But rocks, there are so many variabilities. For example, I know cut sandstone is obviously popular, perhaps in Sydney, but for us here, less so. It's not as easy supplied as the granite boulder. So you do depend a lot on operator expertise, and I actually think that the level of supervision and inspection has to be much, much higher. I think there has to be much more diligence on what you accept and don't accept, because walls do you do put yourself in a very low safety factor situation or worse. So, there is, I have seen an example where membranes, a geomembrane was, HDPE was placed between rocks. I probably don't need to say, but friction doesn't work very good on HDPE. So I think that was kind of an obvious one, but nobody picked it up, and of course it was found out first. Rain found that one out pretty quick. Fortunately, during construction, it was never going to last. So simple things like that you would imagine are obvious, but maybe not so much to others. So I've also just shared there is I found Barton produced a good paper on rock fill density and friction angle. And it shows some variation for different confining stresses. So obviously you get higher stress. This is from rock fill dams. I found that quite a useful way to have more informed decision about what, if you're going to use this rock fill method, what you should use for your parameters. So, I mentioned settlement. So this is one of the serviceability conditions. So we see this a little bit more often than we really would like. Typically, this is a circumstance where we've got a hard structure like a stormwater treatment, detention, or treatment tanks, or access shafts in a smallish gap. Upper round shafts, we can't put obviously large machines, so we're using small compactors. Productivity of those rollers, you can imagine, is not high. Obviously, very strong preference to use fill on the dry side of optimum because it's easier to compact. You can imagine, you can see there's an example of showing where the permeability of that fill rapidly increases once you get up around that 10% voids, which is what you're looking at if you accept 98 with a -2% moisture. You're probably talking those kind of, and you see how rapidly the permeability changes after that. Sodic soils are especially sensitive to this. They will also do that. So on the right there, you can see a real project where settlements are going pretty, that's a long time plot. You can see it's perfectly, after an initial period, it's perfectly tracking for a long time, a creep settlement behaviour. It's in a pavement. That's obviously taken some management for that, but it's heading for 30 years for a pretty good size. So a fair bit of asphalt will be needed there. So again, it's real. Creep behaviour, it's real. It follows, follows the general rules of geomechanics as we understand them. So there's nothing new there in that sense. So, this is the biggest one. Look, drainage is done well in lots of cases. It is the most critical aspect of the walls. If you look back, obviously AI says it, Chris Haberfield's work, you can see it appears, it seems to me that what we're seeing is that the attention to detail, it gets to a point and then the attention to detail or is either lost during design or at the time of construction. So most walls, big walls particularly, are probably going to have a sag point. That's just following topography. I mean, there's going to be a low point somewhere on the site, and that sag point obviously is probably not going to be available to stormwater infrastructure, which obviously, because you're draining the top of the site, not the bottom. So where does that drainage water go? Discharging it out onto your neighbour's property is a bad idea, but that's what we see a lot. Allowing it to pool in there, down at that level, that's not a good idea. That allows softening of the subgrade. There's an example there of quite a well-built wall, but unfortunately the subgrade conditions, clay, after being saturated for quite some time, just eventually gave up and just had a simple bearing capacity failure because of there was no proper treatment or understanding. So I think that you can see Mike Dovey, again, this paper I strongly recommend. Again, drainage arrangements for the GeoGrid product, GeoGrid walls, those are quite important. Incorporating well-engineered drainage arrangements for GeoGrid is important because GeoGrids in clay field won't perform well if you don't well drain them. And water happens, seepage happens, pipes leak, it happens. So, we need to allow for that. I've also put an example of my pad 8. Most of the residential blocks now are so small they can't put a pool in anymore, but putting a fiberglass pool, backfilling it with gravel next to a wall, just another great big subsoil drain. Where's that water going to go? That's a bit of a risk again for sleeper walls particularly. So just again, thinking about the details, what might be needed. The other one I just wanted to, we're noticing more than, we're seeing a little bit more regularly than we should, is to do with sleeper walls. And so, for example, the wall you can see there, that's in very stiff clays. It's got a significant, I think the footing's 4.5 metres deep. The ground hasn't, that hasn't failed as a result of the ground capacity. So I think the issue that we're starting to see now is that, so a bit of theory on lateral capacity of piles. Short pile failure, you can see down there, is where the ground capacity governs. Long pile failure, this is Brom's theory, is where the moment capacity of the pile is the governing capacity, and that's where the yield of the pile yields in moment. So, commonly 150 or probably 200 UCs are used, maybe in a 450 diameter pier. The bending capacity of those is very low. And if you then apply that into bronze long pile theory, you're going to find that the capacity of that pile is very, very small compared to the earth pressures. Where that starts to become even more of a concern is in a tiered wall, where the upper wall's doing a lot of work and it may not be getting a lot of support from the ground, the backfill that's behind the lower wall. That may not be very good. You can imagine there what happens then is the moment the position of that maximum moment moves down, the moment moves up because you've now got a longer moment arm, you're picking up more earth pressure load. Things could go bad quite quickly in that respect. I'm not a structural engineer, but I really think there needs to be more thought given to full cage reinforcements for these piles to significantly increase their capacity. Tiered walls, the other thing we have seen is stormwater. So a number of these walls have problems during construction, and it's often because the uncontrolled discharge of stormwater often goes to the walls. It goes down the back of the wall. The wall has got the drainage systems behind the walls are designed for seepage, not for stormwater. Secondly, for example, in a tiered wall, if it overtops, you're then softening the ground in that middle tier, which again probably hasn't been able to have very high or effective compaction. So I'd say with tiered sleeper walls, that upper tier particularly, don't miss it. Really need to give that a lot of engineer that really well to account for these kind of conditions. One other thing that we have seen as well is situation of a cantilever wall which has a permanent prop in the form of the slab for the structure from the pavement, using it as a permanent prop. But in the interim, during construction, there was no prop applied. And as the delays of construction occurred, the wall, well beyond its capacity, the cantilever started to move, and emergency propping was needed there. I think, to me, if you need propping, you need propping. So put in interim propping. I know there's an inconvenience factor, but these, you're probably talking big walls, and what's a lot more inconvenient than propping is a problem with the wall coming, either affecting you or particularly your neighbour. So I think that would be a case of be careful. So just in summary, things that I think are just sort of better practice principles. So drainage, just understand where it goes, make sure it gets built properly. Don't just say, don't have a view of diligence about that. Really, that's such an important factor. It doubles the load on a wall. Earth pressure is similar to water pressure, is the same as earth pressure, probably in more some cases. So make sure you get that right. Water services are critical, particularly fire mains and major stormwater. They are high risk. You need to make sure those are really thought about in detail. Move them away if you can. If you can't, put in these other measures. Surface water during construction, as I've said, that you must divert surface water. It must have arrangements to avoid the walls. Walls are not intended to cope with that. Sleeper walls, long pile failures, as I've just said, check them out. I think, just make sure you're comfortable that you've got that covered. Tiered walls, obviously numbers of issues there that potentially things that you can't control as well need to be in mind. Rock walls, again, the facing rock method, I think practically there's probably limits to what's doable with what's sizable, and after which I would probably say think about going to engineered type block systems, GeoGrid, for example. Lateral movement is real, and again, settlement, compaction, looking at what you do to try and help ensure you've got better compaction around structures when you've got the wall and near wall, particularly back of walls. And again, the stage, as I said, interim propping. So thank you.
Thank you, Andrew, for your input today. I'd now like to welcome our second speaker, Jamie McQuilliquim. Jamie is a technical director with WSP in Sydney. He has extensive experience in geotechnical engineering, including design and construction of soil and rock slopes, retaining structures, ground improvement, and piled foundations. Please join me in welcoming Jamie McQuilliquim.
Thanks very much for the introduction. I'll be talking about retaining wall failures today, talking a little bit about walls that are embedded into the ground, and an example here of a famous failure of a retaining wall in Singapore that happened several years ago. I'd also like to just acknowledge the traditional owners of the land that we're all joining from, and acknowledge elders past and present. So just as a general overview, just as a start, retaining walls are constructed to permanently steepen the ground. And in doing that, we can move ground from a stable initial state to a non-stable situation, because essentially we're creating a void into which the earth and water can move. Now, many designs, and all designs, have to assume soil properties. Some of them don't give enough attention to some of the safety considerations, particularly for temporary conditions where walls may not be the permanent structure. The impacts to ground and groundwater from temporary support or even long-term support often or sometimes are not well considered. And the result of this is people can make a poor choice of retaining wall, and sometimes design can have some oversights in terms of safety and construction, and the key things being the stability and movement of the excavation. Now, there are different retaining wall types. Andrew has already covered some embankment, so some retaining walls where we're generally building up from existing ground. I'm going to be focused a bit more on excavations where we're cutting down into existing ground. There's different considerations for both of these wall types. For fill embankments, generally you have more control about what the wall is being built from. And so in potentially they should be easier than cut excavations. However, even for low height walls, you do need to be careful to give them the attention that they warrant, because you can still cause some major issues, as Andrew's discussed, with embankment walls. For cut excavations, there can be issues. It is a relatively high risk construction activity. The material that we're retaining is going to be variable. It's natural. We won't know perfectly what's there, and the properties can change with time. We do have to often deal with groundwater, which poses challenges, and we'll go through some of those considerations later in this presentation. There is very good guidance for embedded wall design. CIRIA 760 is a very good reference for anyone who is working in this field, and will cover in great detail a lot of the considerations I'm going to walk through in this talk. So I'd certainly encourage anyone who's doing this type of work or wants to do this type of work to obtain and work through that guidance document. As we've touched on already, embedded walls are a risky business. You are creating a void where the soil and water can move into it. And some of the things that can happen, or some of the failures that have occurred, are a partial or full collapse of the excavation. There can be movement of the wall itself, and then if there's any structures or services near it, they can also move. Groundwater inflow, depending on the ground you're in and the type of wall used, that can be something that can be pretty serious. And if water does start changing and you do have an impact on the groundwater regime outside the excavation, that can then cause other issues for any nearby services or structures. The forces involved are very large, and there's significant consequences if we don't get it right. The examples on the right-hand side are from an embedded wall constructed a long time ago now for some docks in the UK. But some of the modern examples where collapses have happened, like the Nickel Highway in Singapore that was on the cover slide, are somewhat similar. Unlike tunnels, it's not a self-supporting geometry that we're looking to achieve. There's no arching, and usually retaining walls will be less engineered. So what's failure? So really any can range. There can be all sorts of different types of failures. It can be just unsatisfactory performance anytime in its design life. But particularly people tend to focus on those that result to danger to life and damage to the wall itself or any nearby assets. So it could be a collapse or a partial collapse, and that would impact on safety, as we saw in the previous slides. People were killed in that historic example. That's generally where we will be doing stability checks, so ULS type calculations. Serviceability often will govern the design. If there's too much movement, then that's something that can happen quite commonly in failures. And something that does need to be thought through the whole process is how much movement is too much for the temporary structure itself, but also nearby assets. Water ingress, too much water seepage can cause some issues during the life of the permanent structure, or loss of waterproofing can lead to drainage issues and issues with what the client was expecting to receive versus what they do achieve, and potentially a loss of durability of components used in the wall can also be a failure. Now, why do retaining wall fail? The image on the right-hand side is from a journal written by Reason, who basically has the model of slices of cheese, with each slice being a barrier or something that could help stop a failure occurring. And there'll generally be holes in the cheese that may move. And it's really when a number of things line up or a number of causes line up that the failure occurs. So what we have to try and do is make sure that we have good design, construction, and supervision for retaining walls so that we avoid that happening. So some of the reasons a retaining wall might fail from a high level would be an inappropriate type of wall is chosen for this scenario. It might be a poor design, either for the temporary or the permanent works. There could be durability issues with components used to make the wall. Sometimes there could be a poor documentation cause to the design and or construction process. Poor construction practice or poor supervision and quality control. Potentially unforeseen ground conditions that haven't been allowed for in the design. And then finally, things could happen during construction or operation that haven't been allowed for in the design process. Now, some of the things that we do need to consider when we're choosing which retaining wall to use. The design function or requirements. Is it a fill embankment? Is it a cut that we need? What durability requirements do we have? Where's the wall located? Is it temporary or permanent? What design life are we trying to achieve? The stiffness, so the stiffness of the system, how can the wall move and what impact do we need it to have on nearby assets? And water tightness, so what are the requirements for that? Where is the groundwater level and what do we need to do? Key questions mentioned before: are there nearby assets? Can it be constructed safely? Costs is obviously a major driver in a lot of circumstances. And really overall, the key questions that I would ask myself if I'm thinking about retaining walls is, what am I going to do to the ground? And how is the ground going to respond? And if you can answer those two questions, then you're a good way towards a good design. So the first question, what will I do to the ground? So some of this will be going back to basics in a lot of ways, but it is important to get those fundamentals right. So if we excavate into the ground, then that excavation process is unloading the ground. If we're filling for a retaining wall above ground, we're loading the ground. Both of those will result in good things and bad things. So, positive things, there'll be some stable ground movements due to stress changes. There could also be some unstable movements because we're steepening the slope and we may have some near vertical phases that need to stand up. Excavation can also result in change in groundwater pressure through drainage. Depends on the type of soil, depends on geometry, but changes can occur. And so how will these impacts impact surrounding buildings, services, roads, and other assets that may be nearby? That's a key thing we have to assess. How will the ground respond? So will water or soil move? Will water or soil become unstable as a result of excavation? Will there be changes to the groundwater flow regime? And what does that mean? How much water is coming in? Will there be drawdown outside the excavation? And some of those impacts from groundwater can be significant. They can lead to piping, liquefaction, or broader ground consolidation. And they can impact areas quite far away from the actual excavation. So it does warrant careful thought. Now, as we're all aware, stratigraphy in the ground is not going to be horizontal. It's not going to be 2D. Got an example, anchored excavation here, where there could be changes in ground level. The groundwater level may vary across your excavation. There can be quite large changes in depth to rocks. And depending on the construction method you use, you may have soils that may appear similar to rock for some construction techniques. So some key things there in terms of, where are the perimeter walls founded? How can you be sure that you're in the founding strata that you're aiming for? You might have unbalanced forces on either side of your excavation. There could be, a river nearby, which can result in changes to both surface and groundwater levels. So things can quickly get quite complicated. So we do need to just keep that variation in mind. Often we won't have a large number of boreholes potentially with which to do the design. There may be restrictions on where they can be carried out. We may need to work within an existing building or not working within an existing building. So all of that needs to be pulled together in terms of getting a good understanding of the geology and the ground model before we get too far. Now, in the next few slides, I'm going to just talk a little bit about earth pressure, which in retaining walls that are passing through soils is an important and fundamental behavior. So the starting point when we install structure into the ground is that the earth pressures are at rest. And on the graph on the right-hand side, it means we're at the vertical axis, essentially. We haven't started to excavate, and the earth pressures on either side of the wall are balanced at this point. As we excavate, one of the cases that we have is that the wall moves away from the soil, away from the retained soil. And as this happens, we move to the left-hand side of the graph, and there'll be some movement, and the earth pressures will reduce. The amount of reduction will depend on the type of soil that is being retained, but movement is required in order to change those pressures. The alternative is if we have a wall that moves towards the soil, then there will be an increase in pressure, which means that we move to the right-hand side of the graph. And again, depending on the soil type that we have, there'll be a change in pressure. But you can see on the graph that quite large movements and movements even larger than some of those shown on this graph may need to occur before we mobilize that force. So this is somewhere where understanding the response of the ground and what movement is needed in order to generate those forces is a really important factor. And that's something that quite often may have occurred in some of the failures that we'll talk about a little bit later for embedded walls, particularly with as sensitive assets close to the excavation itself. Some other fundamental assumptions that we bring into retaining wall design are around soil strength, stiffness, and earth pressure. So as we've talked about just before, K0 is not soil property, and it depends on the stress state of the ground and the geometry that we have. It will be between K0, Ka, and Kp, and K0 is not usually known. In soils, because they are have a relatively low stiffness, it means that usually quite large movements may be needed in order to change the stress state, as we just saw. So we'll need some movement to happen to reduce the pressures down to Ka if the wall is moving away from the soil, and very large movements to generate passive pressures if the wall is moving towards the soil. Now, the bounding properties can be usually reasonably estimated from drain strength parameters. That doesn't mean need some quite high quality and quite high quality strength testing to be carried out. The other method that is commonly used is to use correlations from other tests, like plasticity clay. But once you do get into very soft or soft clays, you do need to be careful in assessing those values. When we're assessing earth pressures, we do need to be careful about using cohesion. It can be quite variable and will dominate the strength at low depths. And what can happen is if you use large cohesion values, then the excavation may theoretically be able to stand without support. And so you may be designing with a relatively low pressure assumption. The other thing we have to be careful about is apparent cohesion due to suction. That's something that can change quite quickly and can lead to collapses, particularly in situations like open trenches. So it is something that I would encourage you to be very wary of. If we move on to rock, so often excavations will pass down through soil into rock units. K0 isn't a property, or the pressure within rocks is not necessarily a property similar to soil, and it can vary with direction and location. In Melbourne, there's a difference in some of the pressures within the siltstones, and there'll be a higher stress in the east-west direction compared with north-south. In Sydney, it's different again. Higher pressures again in Sydney than in Melbourne. And there can be some quite high locked-in stresses in the sandstone in Sydney, with larger forces generally being in the north-northeast direction. And those pressures will result in movement. The benefit with rock is that they do generally have a higher stiffness, and so maybe smaller movements than we would have for an equivalent situation in soil. However, things to be careful of in rock is that it's really the planes of weakness and the major structure in rock that governs its behavior. So we do need to understand the bedding of the rocks. If there's a dipping in the bedding, then that's something that's really important in designing basements. The soil-based estimates of Ka, Kp are probably not applicable, and there can be weak planes within rock, and some of them sometimes can be quite low strength. So essentially, although you're working in rock, you're using strengths that are used in soil mechanics. So you can have weaker and higher earth pressures in rock than you would in a very soft clay in certain combinations. Water is often a key contributor to instability. Jack Morgan, who's shown in the picture on the right-hand side, had a saying of no water, no worries. It does have a significant effect on everything we do. It affects stability, it adds pressure to walls, it impacts soil strength. It can impact how you can build ground anchors and how they may perform. And seepage or water flow has some significant impacts on excavations. So commonly what will be done is try to make sure you have enough drainage, both for surface water and groundwater. looking to try and seal the surface to avoid surface water becoming groundwater where you can. Looking to achieve an adequate cutoff, so the walls of an excavation going sufficiently below the bulk excavation level to control the rate of groundwater flow into the excavation, or sealing into an impermeable strata in some circumstances. If that isn't done, then, as we've touched on before, there can be quite large-scale impacts from the excavation that can impact other assets. And you do need to think about whether active pumping is needed to help bring down the groundwater level, or whether you just need some pressure relief in the base of an excavation. And drained and tank basements, both are worthy of a separate presentation, but you do need to think about, for each of those situations, how the excavation will be sequenced and what the impact on groundwater will be. A topic on its own right. Now, depending on how we want to try and manage water inflow into our excavation, there are a range of different wall types that can be used. There are some examples and case studies a little bit later that go through some of these. And as we move down the list that's shown there, there are fewer wall joints and less water will be able to get through the wall. You still need to work out where the wall is founded, and whether there's potential for water to come up from units that are below the wall. But in terms of flow through the wall itself, D walls obviously are relatively tight. Some of the soldier piles and shotcrete or precast panel walls are relatively leaky. So choosing the wall does depend on geology, depends on the water tightness you need, and it depends on the finish that the client is expecting. Now, in terms of wall embedment is needed to achieve lateral stability. It's needed to achieve cutoff of water. It's needed for vertical stability, particularly if we are using ground anchors that are inclined. And base stability, again, that's tied to the water inflow into the excavation. Now, when we specify a founding layer for the perimeter walls or for a retaining wall, a key question is, how do you actually confirm that you're in the correct strata during construction? Because it's important to think about the consequences if embedment isn't achieved, and that could be for, that could impact any of the items above we've just talked about. You do need to be very careful in alluvial materials, which are by their nature very variable and saturated and can change quite quickly. In rock, piles don't necessarily always need to extend below the base of the excavation, but you do need to think about how the loads from those piles will be carried and how the rock below the piles will be supported. Now, one of the topics that has led to basement failures, particularly with groundwater inflow, is around verticality of piles. AS 2159, the Australian Piling Code, does not cover retention piles, and there's no codified verticality standard for design. So do you warn your clients? In doing this, we do need to think about pile spacing and what contractors can actually achieve in the field. There are some typical values here. Piling contractors may have their own thoughts on these, but here are some guidance numbers on what can be achieved typically. So for CFAs, typically 1 in 75. If very good quality work's being done, maybe 1 in 100. But there are quite specific factors that can vary what is achieved. As we go to a heavier drill string, like case board piles, you may get higher quality verticality, as you can see in the numbers here. And D walls, typically 1 in 100, can go up to 1 in 400, a bit like the case board piles. The consequences of loss of verticality or misalignment can be architecturally, the finish doesn't look great in a basement. You can lose overlap, which can lead to water flowing between the piles, and that can lead to seepage, piping, or soil loss. And worst case, you could result in a loss of basement space, either through having to have facing panels with additional drainage behind it, or if there's redesign, as we'll see in some cases a bit later, you may not be able to go as deep as you hoped with your excavation. So just an example here of a secant pile wall where we've got 600 mil diameter CFA piles at 450 mil centers. So we've got 150 mil overlap, and if we assume the verticality is 1 in 100, which is quite high quality piling, the amount of overlap we may still have depends on how deep the piles go and how deep the basements are. So 1 level basement, we've probably still got about 90 mil overlap. 2 levels, we're down to about 30. 3 level basement, there's potential that we've lost our overlap. So typically 2 level basements might be okay, 3 potentially, but there's a chance you're going to get leakage after that level. And so the other thing, often the piles will be found below the basement level, and it's still important to try and avoid water flow through the ground below the base, particularly if you had saturated sands. So a comment there, what you see can't hurt you, but you may see increased water flow in parts of a basement. The other thing that can happen with secant piles is if there's delays in piling between soft and hard piles, then that can also impact the verticality that can be achieved and the seal achieved between piles. So just something to think about when we're thinking about the piling method to be selected. Ground anchors are often used to support excavations. They can be passive or active. Quite often, if anchors are used, they are post-tension because that helps reduce movements. The fixed length of those anchors needs to be outside the active zone of the wall so that they are founded in stable materials. And once you go beyond about 8 or 10 meters in length, then the resistances that will be achieved are lower. However, there are single bore, multiple anchor options available that can be good if you're looking to try and spread the load over a longer length. Installation in sand, particularly below the water table, can be difficult. You may need temporary casing. If you do try and install anchors without casing, then there are issues around having a separate free and fixed length. So we're looking to fix the anchors in at the end point of the anchor. If there isn't grouting in 2 stages, then potentially you lose the free length and you may be transferring load in part of the anchor that you were assuming does not, and that can lead to issues that we'll touch on a bit later. The life and durability requirements for anchors, so how long they need to last, whether they're temporary or permanent. Records with anchors are varying quality. It is essential for anchors, particularly permanent anchors, that good details are kept of the drilling, testing, and finishing activities. And the whaler and connection details that are used are also fundamentally important to their success. Wall finish. So this is something that is important to the client. It's what they're going to see when they walk into their completed basement. It's something that can cause disputes, particularly where somebody was expecting something but received something else. And with this, generally picking a cheaper piling option or a cheaper retention option will generally have a poorer finish. The different options we had for different wall types earlier in the presentation, they are cheaper to install, but they will have more water flow through them, and that will lead to a poorer wall appearance. So if you do pick a poorer option, then you may need to have a plenum wall with drainage hidden behind it, but you lose space in the basement as a result of that. If the walls are out of alignment, then if it's out of alignment facing into the basement, you may lose space that you were thinking you had. And so there is a bit there where sometimes, depending on the depth of the basement, more expensive options will result in a better finish and an overall better outcome for the client. There's obviously water staining and leakage that could occur later in the life of the basement. and you need to do something with the water that flows into the basement and manage and dispose of it. In terms of support systems and anchors or other methods of supporting the basement walls, there are two general types of systems. There are passive systems, where the restraining force is generated through movement, similar to some of the graphs earlier in the presentation. They'll generally result in walls that will move more and cause potentially greater impacts to adjacent properties. If they are close to sensitive assets, then they probably shouldn't be used. Examples could be gravity walls, cantilever walls, reinforced earth walls and sawmill walls that we won't touch on too much in the presentation. But with any types of those walls, you do need to really think about what's near them and what the impact of the movement is going to be. Where active systems are used, then we do use post-tensioning or jacking of props in some instances to help limit displacements. The forces used need to be selected in order to control movement, so it's a movement control, and stability is maintained as well. Now, these are generally designed to resist a higher earth pressure because we don't get movement of the walls to reduce the pressures down to the active state. And examples of them would be anchored systems with soldier piles, kinetic pile walls, or diaphragm walls, or props that are jacked out. Just some pictures here that we'll go through reasonably quickly with some of the different wall types that can be used. Some of the types that are installed before excavation incurs would be, soldier piles or contiguous piled walls where the spacing of the piles varies. Again, depending on the water inflow and the type of ground, you'd need to be careful in using them in saturated sands. Secant piles, so either hard piles that would be drilled using casings or hard soft piles. Sheet pile walls or diaphragm walls. So just some pictures of the different wall types. Some of the passive support systems that I touched on a couple of slides ago. So rock bolts will need to move in order to generate the force that they're assumed to have. Struts, if they are not hydraulic or able to be pre-stressed, will be a passive system, and that there'll need to be some movement of the walls in order to generate forces within those struts. Some example and pictures of anchored support systems for embedded walls. And in terms of anchor forces, you do need to be careful with them. If you adopt anchor forces that are too high, you can try and pull the wall back into the soil, and that will result in a move towards some passive pressures and potentially higher forces acting on the wall. So it can be important not to have anchor forces that are too high. Ideally, we get them just right and a nice balance. So some of the things that we need to ensure during construction to make sure that things go well. Documentation needs to be detailed enough so that people can build the wall as it's been designed. Specifications do need to be detailed and targeted on what's to be done. And if there's any key construction stages, it's important that they are clearly described and shown so that people can understand the sequence that's been assumed. So key components need to be identified, tested, and confirmed. So ground anchors being a good example. They should always be tested, and the records from them should be kept available as they are critical parts of the overall system. Likewise, pile construction records, toll levels, confirmation of founding strata, all really critical to the performance of the system. And whalers should be used on embedded systems where anchors are used. So there are issues if construction and supervision and QC is neglected. It's important to have people checking that the plans and specifications are being followed, that where documents are produced, whether it's anchors or piles, that they are documented and checked and accurate. And monitoring of movement is critical in deep excavations, and that should really be proactive and provided to the designer so that if there's unexpected behavior, it can be identified early and responded to. Ideally, there's a monitoring plan ahead of time to identify behavior that's expected and behavior that's not expected in order to be able to take action to avoid issues, as I'll touch on in some examples shortly. Unforeseen ground conditions is something that can lead to issues with retaining walls. But there is a question on what's truly unforeseen, or have we just done a poor investigation? In the past, movements of retaining walls have occurred due to low strengths that are lower than reasonably expected. So there are cases that are out with the normal experience. You can have higher in situ horizontal stresses than you'd expect. And what happens if you don't have any in situ stress measurements? And there could be unknown ground conditions outside the site, or things have changed where you haven't managed to investigate. So ideally, you have got a construction method that can be adjusted and capture those changes. Did present earlier, or mentioned earlier, that sometimes there are future events that aren't included in the design. So it could be a water main fails near the site and a groundwater level rise results. And so that's something that should be considered and designed for. Accidental over excavation is something that CIRIA talks about. And then the other thing is an impact of an individual strut or anchor failure on the overall system. And so some of that came out of previous failures where I guess the resilience of the overall system did not react well to loss of an individual component. So that's something that it's good to understand the resilience of the overall system. Going to run through some examples here of projects, both in Australia and overseas, just with some examples of failures of retaining walls and generally what caused them. Provided some information on each one, but not necessarily exactly where the site is. So there was one project here that we're showing where, as a result of poor anchor installation and over excavation, there was some wall movement that led to damage of some adjacent buildings. Work was stopped and an emergency order was placed on the excavation, which was only able to be recommenced after some temporary strutting was installed to help control the movements. So again, movement being a key thing, and something unexpected, the over excavation. On another project, there was a kind of soil mix wall. One of the options that down the lower end of the list in terms of water ingress, so quite a good option for that. In this example, there was quite a good site investigation and a reasonable knowledge of the ground, but there were some optimistic assumptions in the assessment of ground anchor capacity and behavior. It was a 2-level basement with a 6-meter retained height. And at one stage in the project, the toe embedment of the wall was reduced from 6 meters to 4.5. Bar anchors were used in order to provide some support to the wall, and they were installed into interbedded sand and clay alluvium. After excavation commenced, there was 300 to 400 mil of horizontal wall movement. Emergency propping had to be installed, and the overall outcome was there was damage to some adjacent properties and pavements, and a redesign of the structure was needed because the wall had moved such that the superstructure had to be adjusted to allow for the new perimeter wall locations. And the figure on the left is from the CIRIA document I mentioned earlier, and displays this as one of the mechanisms that should be assessed. So again, being careful about how anchors are modelled and making sure how the anchors are modelled matches how they're built and how they'll perform. This is an example of a basement in alluvium below the water table, so similar geological conditions to the previous stage. There was probably insufficient investigation and knowledge of the ground in this instance, and some optimistic parameters used for soil, the anchor capacity, but also the pile verticality. As a result of this, there was insufficient pile overlap, and the pile embedment was too short. There was significant water ingress and loss of base of the excavation. There was anchor capacity not achieved, and the walls moved, leading to damage to surrounding assets. So as an overall outcome, the fourth basement level that was proposed originally was lost, resulting to impact to the structure, as well as the damage of the adjacent assets, being something that had to be addressed by the project team. One thing with inclined anchors, where you have them, is in pre-stressing those anchors, you're introducing a downward force into perimeter piles. So we do need to be very careful about the socket of those piles and making sure that they're socketed into stable ground that can take the vertical load that will act on them. And just a picture on the right-hand side where the material below the base of the pile, possibly debris from construction, was quite poor. That can lead, and did lead, to settlement of that pile and anchor relaxation, so less force in the anchors, which can lead to increased lateral movements as additional lateral movement is needed to put tension back onto the anchor again. Do need to be careful if there's knowledge in areas of existing instability or landslips being prevalent, or geological conditions that may be conducive to landslips. Then relatively small excavations could mobilize an existing slip, whether that's walls being embedded piles, or whether it's walls going up where a small excavation is needed. It's really important to identify those potential conditions in an area or on a site. A very large scale landslip that's shown in the right-hand image was initiated by a relatively small excavation for a low height wall and led to loss of a significant number of properties. Low strength bedding was something I mentioned before. Within rocks, behavior and large movements can occur if there are low strength bedding planes. This was an example of a basement where bedding plane sitting at about 22 degrees led to movement of an anchored pile wall. It wasn't able to be easily seen in rock core, and so that was where monitoring of the excavation with inclinometers was really important to identifying that feature. It was identified in the left-hand image. You can see as a buttress was constructed in order to stabilize that rock wedge, and additional anchors then installed to provide sufficient resistance to hold that rock wedge in place. So groundwater issues that can occur. This project was a site in an alluvial floodplain quite close to a river. A sheet-piled excavation didn't achieve cutoff into a clay layer, and as a result of that, there was piping and sand boiling at the base of an excavation, which was about 10 meters below existing ground level with a relatively shallow groundwater level. That boiling, or the inflow into the excavation, led to ground loss and damage to an adjacent brick building, and the excavation had to be flooded to stop the instability of the excavation and to prevent that sand boiling. Some fairly significant remedial works were needed. The floor of the excavation was concreted and temporary ground anchors installed to help stabilize the base, and significant amount of grouting was needed around the perimeter of the excavation to help restabilize those buildings. A similar example from a contiguous secant board pile project. Again, you can see the sand boiling in the left-hand image there, and this was a situation where there was insufficient embedment or an insufficient weight in the base of the excavation left, and pressure on a clay layer that led to loss of the base and remedial work being needed. More broadly, as we touched on the verticality, water inflows into basements are problematic. Water will tend to try and find its way wherever it can. So temporary anchor holes, joints in wall piles, anywhere really there's a weakness in the wall. That can lead to effects, obviously, within the basement in having to manage that water, the visual impact that we touched on earlier, but also impacts outside the wall. So lowering of the groundwater table can lead to settlement of adjacent buildings. So some closing comments. Retaining wall failures are common. It's usually because of poor choice of the type of wall that's being used. It might be optimistic or incorrect design, lack of knowledge, potentially poor construction. It occasionally can be catastrophic. We had some pictures on the cover slides and also the old dock that collapsed. They're thankfully rare, but the consequences that we're dealing with are high. So it's very important to understand the geological setting we're working in, how the groundwater conditions are going to respond and what's around you. So if you're in an urban environment, there's a very good chance you have nearby properties, nearby services. So protecting those existing assets is really important in picking the retaining wall options you're using. Choosing the right type of wall is important. Being prudent in doing that and giving good advice to clients to make sure that their expectations are achieved. And overall, it is a risky business, and so please give them the attention that they need. Thank you very much.
Thank you, Jamie. Well, now it's our audience's turn to get involved. So please don't forget to ask our speakers the questions via the chat box. Unfortunately, Andrew is unable to make the Q&A, but however, I'm very pleased to welcome Walter Mattenbroek, Director, Principal Geotechnical Engineer from Core Consultants, to our Q&A session today. Now, a big thank you, I have to say, to everyone who submitted questions on registration. So what I might do is start with one of those questions. And Walter, I'll bring you straight in. And the question is, and it's come through from James from New South Wales, and he asks, how do you design for accidental hydrostatic pressure? Even if a retaining wall has subsoil drainage, should we be designing for water to a level of, say, half the wall height? I have him on mute.
Thanks.
All good.
All right, thanks. It's probably a site-specific thing, that one. I think TMI requires a design for groundwater level at 1/3 of the wall height, which is probably appropriate for an important or movement-sensitive structure. But really, you want to risk assess that, based on the context, the ground conditions, what groundwater level you might expect, and also the risk based on what's upslope or downslope of the wall. And of course, the groundwater level would be a raised groundwater level would be a temporary condition, so a factor of safety of 1.3 would be appropriate for that.
Thank you. Jamie, just I could see a few questions coming through live, so I might jump to some of those. There was a question which came in from Stephen, who's watching, and his comment was, both speakers rightly attribute the main causes of retaining wall failures to water and soil properties of backfill. Is there an Australian guide on retaining wall design against PGA due to seismic event?
Yep. Thanks, Megan, and thanks for the question. There is an Australian code, so AS 1170.4 covers earthquake design, and that extends to retaining walls. It is a subject where earthquakes do happen in Australia. There was the Newcastle earthquake 20 years ago or so. And so it is important to work through that and understand that seismic design or seismic events do happen in Australia. And they tend to be quite long return period events, but can be quite large. So it is an important design consideration that people should take through.
Awesome. Thank you. I'll jump in. We've got quite a few live questions. So there was one which I might pose to you, Walter, and it was, what is the lifespan gabion? If I've gabion baskets. How safe are these retaining walls? Is there an impact with the metal if it becomes rusted?
Oh, yep. Yeah, so the design life for a gabion would depend on the spec of the wire mesh, and then the environmental context or setting. And for a typical galvanized wire mesh, design lives between 20 and 50 years. But it's in coastal conditions, I think that could be a lot less. I've seen gabions fail in less than 5 years, maybe 5 to 10 years, because of corrosion on the metal, and of course if the mesh corrodes or breaks, then the wall will fail. So it's important, I think, with gabions to just take into consideration what specification is on the mesh and what the context is of the wall in terms of exposure to salt or water.
Thanks, Walter. Jamie, there was a question that came through around zero boundary sites. So it came through design engineers with zero boundary sites often fail to consider the impact on existing boundary retaining walls and adjacent structures, which can lead to retaining wall collapses or damage to the adjacent structures. So I suppose the question is around the role that the engineer plays with regards to the responsibility of the actual builder.
Yeah. I mean, I think identifying the constraints all around a site, and part of building the ground model is understanding what existing basements are nearby and how they're constructed. That can be difficult to find sometimes, but certainly through site inspections, trying to get plans or records of adjacent buildings, it's a fundamental part of the design. And so certainly, if you are working in an urban environment, understanding if there's tunnels, services, existing basements, or existing foundations is all part of the design. There will be circumstances where things are unexpected or are not found, but certainly doing a good desk study and trying to find that during the design period is the time where it should happen, in my view.
Thank you. So Walter, there was a question which came through from Liang from Victoria, and was just asking what other drainage methods can be used besides ag pipe?
Yeah, probably ag pipe is ag pipe in gravel or pipe in gravel is the most common. You could just use coarse gravel. There's probably some proprietary products that you can use, but gravel pipes in gravel are probably the most common types, and so probably the important thing to remember is to design it, the drainage to have like redundant capacity to cope with, get rid of water quickly, and also to be, not require maintenance if possible, because that's often not done. And then if you get a failure of the drainage, then it can lead to problems. Try and make the drainage as robust as possible, which is probably why pipes in gravel are pretty common.
Well, I think that's probably the very next question that I had was around the importance of drainage behind walls to relieve pore pressure. I suppose that is continuing on that answer. Yeah,
drainage is critical. It's everything, because as Andrew alluded to, so many types of failures are, involve water in some form or another. So, drainage is probably one of the most important things, and it's often something that's a bit, it's often well specified. I think Andrew mentioned this, but the discharge points are sometimes not specified really well in a design, or it's left up to the contractor or during construction to finish off the drainage outlet, and that can be really important, but sometimes not specified well. So drainage, including where the water will go, is very important.
There was quite a number of questions around the Australian standards. So I'm not quite sure, maybe either of you would like to maybe comment upon maybe what Australian standards we should be directing the audience to. Or not?
Yeah, Australian standard 4678, I think, is the one that relates to retaining walls, and it's got guidance on soil parameters. I think there's an update coming, but I don't have specific knowledge on that right now.
Yep, and sometimes, yeah, in addition to 4678, Syria Guide 760 for the embedded walls I was discussing is a really good tool. There are obviously differences. That was written from a UK perspective, and so it touches on Eurocode, but across a lot of the design codes, they do adopt similar limit state or global lumped factor of safety approaches with some flexibility still. Obviously, there has been a push across a lot of standards now to move to a limit state approach rather than traditional factor of safety approach.
Awesome. Look, thank you both for that. And I have to say, I think we've already run out of time with our Q&A today. I could see there was so many questions coming through, but look, a huge thank you to everyone who, our speakers who are involved with today's webinar. So please join me in thanking Andrew Middleton, Jamie McQuillican, and Walston Massenbrook for their time and input. We really do appreciate your time today. I would also like to thank Engineers Australia's industry partner, Brickworks, for their support with the webinar. I am pleased that we do have more webinars in this series, with our next webinar, Design of Large Format Retaining Wall Block Systems, happening on the 12th of March, with registrations now open. And then we have our next one around design using concrete sleepers and panel walls. So yeah, looking forward to seeing everyone at those actual webinars. I am also pleased to confirm that Engineers Australia does have a short course coming up on the design and construction of retaining structures that I'd like to highlight. If your team has 8 or more people, we can customise this course for you. Simply scan the QR code and submit an inquiry via For Business tab. Otherwise, registrations are now open for individual members. And my final request is if everyone could please complete the short feedback form, which is linked in the description box below. As you know, that feedback really does help us to improve and plan for future sessions for you, our audience. So if you could do that, I'd be most appreciative. And finally, a big thank you again for joining us, and we hope to see you at our next Industry Partners event. Good afternoon.